Hi everybody, and welcome back from spring break. Sorry it's taken me so long to get a lecture together, but I hope you'll like this one. Remember when we left off, we were talking about Diophantine equations. And a Diophantine equation is an equation that allows only integer solutions. So each solution, an ordered pair xy, must be such that both x and y are integers. And remember that prior to spring break we had developed a technique using Euclid's algorithm for finding the greatest common divisor of a and b. Let me say that again. Prior to spring break we had developed a technique using Euclid's algorithm for finding the greatest common divisor of a and b, of finding an ordered pair of integers xy that was a solution to the Diophantine equation ax plus by is the greatest common divisor of ab. And we call this solution a particular solution. There are actually infinitely many integer pairs xy that are solutions to this equation. So one solution will just be a particular solution. And again, we're going to use Euclid's algorithm for finding the greatest common divisor of a and b in order to find a pair of integers xy that's a particular solution to this Diophantine equation. Our current goal is to formulate the general solution of the Diophantine equation, ax plus by equals the greatest common divisor of a and b. The general solution consists of an ordered pair of formulas, one formula for x and one formula for y, given in terms of a single parameter t. A specific value of t generates a single particular solution. The set of all integer values of t generates the entire set of solutions to the Diophantine equation. So essentially, the general solution to this Diophantine equation is the set of all solutions to that Diophantine equation. Before we formulate the general solution, we'll review the process of finding a particular solution of the Diophantine equation ax plus by equals the greatest common divisor of a and b. And let's look at this example. Find integers x and y such that xy is a solution of the Diophantine equation 945x plus 200y equals the greatest common divisor of 945 and 200. If this looks familiar, this was actually an exercise on our first test. And we're going to perform the division algorithm, letting the larger of these two numbers be the dividend, and letting the smaller of these two numbers, 200, be the divisor. So the larger number, 945, is the dividend. The smaller number, 200, is the divisor. It's not necessarily always the case that A is the dividend and B is the divisor. We have to let the larger of these two numbers, in this case 945, be the dividend, and the smaller of the two numbers, 200, be the divisor. So we apply the division algorithm, and in each succeeding step, we let the divisor in the previous step be the dividend in the current step. And we let the remainder in the previous step be the divisor in the current step. And we apply the division algorithm again. And we keep doing this until we get a remainder of 0, which will always happen eventually. So let's see, repeating again, we take the divisor of the previous step and let that be the dividend of the next step. We take the remainder of the previous step and let that be the divisor of the current step. And we do it again. We take the divisor of the previous step and let it be the dividend of the current step. We take the remainder of the previous step and let it be the divisor of the current step. And by the way, let's check and make sure these actually do work. 55 is 1 times 35 plus 20. And remember, the remainder always has to be less than the divisor. Okay, next step. We let the divisor of the previous step be the dividend of the next step. We let the remainder of the previous step be the divisor of the current step. And does this work? 35 is 1 times 20 plus a remainder of 15. Yeah, that works. Okay. Continuing, we'll let the divisor of the previous step be the dividend of the current step. Remainder of the previous step be the divisor of the current step. 20 is 1 times 15 plus 5. Yep, that works. Okay. And then finally, we let the divisor of the previous step be the dividend of our current step, and remainder of our previous step be the divisor of our current step, and we get a remainder of 0. Oh, thank goodness. The last non-zero remainder, this thing, the last non-zero remainder, is the greatest common divisor of the two numbers. Now, to find integers x and y such that ax plus by equals the greatest common divisor of ab, we reverse the process. And specifically, we go to the equation that yields the last non-zero remainder, that's this thing, and we call it equation 1. Then, moving backward, we label the predecessors equation 2, equation 3, equation 4, equation 5, oh, and finally we're up here at equation 6. That's a lot of equations. Now, starting with equation 1, we express the remainder, 5, in terms of the last two divisors, 15 and 20. So that's next on the agenda. Starting with equation 1, we take the remainder and we express it in terms of the previous two divisors, 15 and 20. So here we have the remainder expressed in terms of its two divisors, and we get this relationship from equation 1. See, here's equation 1. 5 equals 20 minus 15. Okay. Now next, we use equation 2 to express the smaller of the two divisors, in this case 15, in terms of its two immediate predecessors. So we're going to go to equation 2, and we're going to use equation 2 to express these two divisors Well, in particular, we're going to use equation 2 to express the smaller of the divisors, 15, in terms of its two immediate predecessors. Let's take a look at equation 2. Here's equation 2. The divisors are 15 and 20. We're going to express 15 in terms of its two predecessors, 35 and 20. So this will yield 15 equals 35 minus 20. Okay? So from equation 2, we get the divisor 15 expressed in terms of its two predecessors, 35 minus 20. And then what we do is we substitute this expression for the smaller divisor 15 into the previous equation. So here we have an expression for 15, 35 minus 20. We're going to substitute that for 15 in the previous equation, giving us 5 equals 20 minus 35 minus 20. And then we simplify a little bit. And we have 5 written in terms of the divisors 20 and 35. So now what we do is we move up to equation 3 to express the smaller of the two divisors, 20, in terms of its two immediate predecessors. So we go to equation 3, right here, and our goal is to take 20 and express it in terms of its two immediate predecessors, 35 and 55. So we can express 20 as 20 equals 55 minus 35. So let's write that down. 20 equals 55 minus 35. And what we're going to do is we're going to take this expression for 20 and substitute it into the previous expression. We're going to take 55 minus 35, substitute it into the previous expression for 20. So where we have a 20 here, we put 55 minus 35 here. And then we simplify. Let's see, we have 2 times the divisor 55, and we have 2 times negative 35, minus another 35 is minus 3 times 35. And notice when I simplify, I'm careful to keep the divisors distinct. I want to keep 55 and 35 distinct here. Now, using equation 4, we're going to express the smaller of these two divisors, 35 and 55. The smaller of the two divisors is 35. We're going to use equation 4 to express 35 in terms of its two immediate predecessors. And what would that be? Let's see, here's 35. Its two predecessors as far as divisors go are 55 and 145. So we're going to use equation 4 to express 35 in terms of 55 and 145. So that will give us 35 equals 145 minus 2 times 55. Okay, so there we have it. 35 equals 145 minus 2 times 55. And we're going to take this expression for 35 and substitute it into the previous expression for 35. That is, we're going to take 145 minus 2 times 55 and substitute it into this expression for 35. So where we see a 35 up here, in the same equation we have 45 minus 2 times 55 down here. And we're going to simplify that. And when we simplify, this is what we get. No, that's not what we get at all. I'm missing a sheet. Yes, okay. When we simplify, this is what we get. Let's make sure it works now. We have 2 times 55, and we have minus 3 times minus 2 times 55. Let's see, minus 3 times minus 2 is 6. So this is 6 times 55, plus 2 times 55 is 8 times 55. And we have negative 3 times 145. So when we simplify and keep the two divisors 145 and 55 distinct, that's what we get. Well, guess what? Now that we have this equation, we're going to use equation 5 to take the smaller of these two divisors, 55 and 145. We're going to take the smaller of the two divisors, 55, and express it in terms of its two immediate predecessors. So let's go back to equation 5, and let's see what we have. Equation 5, we have 55 equals 200 minus 1 times 145. Okay, so that's how we rewrite 55 in terms of its two predecessors. 55 equals 200 minus 145. So we write that down, and then we're going to take this expression for 55, and we're going to plug it into the previous equation right there. So where we see 55 up here, we're going to take 200 minus 145 and plug it in. And when we do, this 55 becomes 200 minus 145. And then we simplify a bit. Let's say 8 times 200, and we have 8 times negative 145 minus 3 times 145. That's, let's see, negative 8, negative 3, that's negative 11 times 145. There, we simplified the equation, but we've kept the divisors distinct. Okay, we're almost there. Now, using equation 6, we're going to express the smaller of these two divisors, 145, in terms of its two predecessors. Let's go to equation 6. We're going to take 145 and express it in terms of its two predecessors, 200 and 945. So this will give us 145 equals 945 minus 4 times 200. Let's write that down. That's going to give us 145 equals 945 minus 4 times 200. And we're going to take this expression for 145 and plug it into the previous expression. So where we see 145 up here, we're going to substitute 945 minus 4 times 200. So 145 becomes 95 minus 4 times 200 down here. And we simplify, keeping the divisors 200 and 945 distinct. And let's see, we have 8 times 200 minus a negative 4 times 200. No, that's not right. Let's see, this is negative 11 times negative 4 times 200. So that's positive 44 times 200. Plus 8 times 200 is 52 times 200. And then we have negative 11 times 945. Ah, there it is. We have 5, the greatest common divisor of 945 and 200, represented as a linear combination of 200 and 945. Are we done? No, we're not. There's something that we have to be very careful to do. This is important. It doesn't seem like it's all that important right now, but it really is important. We have to take this equation and rewrite the equation so that it fits the exact form of the original equation, ax plus by equals the greatest common divisor of ab. The original equation was of this form, ax plus by equals greatest common divisor of a and b. We want to take this and rewrite it in exactly that form, including we want this to be a plus sign. So let's see. Here's our a, 945. So a times x, that's negative 11, plus b, which is 200, times y, 52, equals 5. So now it's in the form ax plus by equals greatest common divisor of a and b. And one thing that this tells us is that xy equals 11, negative 11, 52 is a particular solution to our Diophantine equation. For future reference, we'll remember that negative 11, positive 52 is a particular solution to our equation. And remember also that we want to take our result and rewrite it so that it fits the form of the original equation exactly. ax plus by equals greatest common divisor of a and b. One of the reasons that we do this is just so that we don't accidentally switch roles of x and y, which is possible. And another reason that we do this is so that we have a plus sign here, and instead of getting the correct value of x or y, we get negative that value instead. So making sure that we rewrite the equation so that it fits exactly the form ax plus by equals greatest common divisor of a and b is important. Make sure it fits exactly this form. Okay. Onward and upward. Something else that we saw before spring break. If we have the Diophantine equation ax plus by equals c, then we call the equation ax plus by equals 0 the complementary equation. What's the difference between the two? We just take the right-hand side and set it to 0 to get the complementary equation. And remember also, given the complementary equation, ax plus by equals 0, the ordered pair, x equals b over d, y equals negative a over d, is a solution. And here, d is the greatest common divisor of a and b. Furthermore, the entire set of solutions of the complementary equation consist of all whole number multiples of this solution. So take the entire set of solutions. The entire set of solutions of the complementary equation are of the form xy equals b over dt minus a over dt, where t is any whole number. So what that means, given the complementary equation 945, there was something else I wanted to mention before this. Let me just say it. If we have t equaling all integer values, this will yield every single solution to the original complementary equation. So, take b over d negative a over d, and take all whole number multiples of this ordered pair. That generates all the solutions of the complementary equation. Now, getting back to something that we did earlier, that we had 945x plus 200y equals the greatest common divisor of a and b. So consider the related complementary equation. 945x plus 200y equals 0. Well, the entire set of solutions is b over the greatest common divisor, t, and minus a over the greatest common divisor, t. So let's see, this is b over d, where 5 is the greatest common divisor, negative a over d, where 5 is the greatest common divisor. For all values, all integer values of t, simplifying, xy equals 40t, negative 189t, or maybe I should say x equals 40t, y equals 189t. For t equals negative 2, 1, 0, 1, 2, 3, 4, 5, 6, off into the sunset. That generates all of the solutions to the complementary equation. So let's say we take negative 2 and plug it in for t. We get the solution 40 times negative 2, negative 189 times negative 2. Take 1, plug it in here, we get 40 times negative 1, negative 189 times negative 1. Another solution. Take 0, plug it in for t, we get 40 times 0, negative 189 times 0, and so forth. If we grind these out, these are some of the complementary solutions. This is a complementary solution when t is negative 2, complementary solution when t is negative 1, complementary solution when t is 0, complementary solution when t is 1, complementary solution when t is 2, and so on and so forth. And let's just plug these things in. If we plug in this ordered pair for x and y, we get negative 75,600 plus 75,600 gives us 0, which is what we're supposed to get. Similarly, if we plug in the other solutions, and I encourage you to do this, we're going to get negative 37,800 plus 37,800. If you would, just verify